Okay. Very good. So this week's particle theory seminar is being given by Bruno De Luca, all the way from sunny Stamford, and we'll be talking about bounds on spin-2 KK fields.
Thanks, and thanks a lot for the invitation. It's an honor to be here to speak in front of you. Yes, so today we're going to talk about bounds on the spin-2 Kaluza Klein fields, and this is based on some recent and ongoing work with Alessandro Tomasiello and two mathematician friends, Niccolo De Ponti and Andrea Mondino. And it also started from some early discussion with Clay a while ago. And cool, so the Kaluza Klein spectrum. So what is it? If you have a theory with extra dimensions and you're thinking of compactifying some dimensions so that you get a lower dimensional physics, then you can find that starting from a higher D field, say even a massless scalar field in higher dimension, then upon compactification you get a tower of fields with in general some masses in your lower dimensional theory, and these are called Kaluza Klein particles. And in this setup, you can, in such a scenario, you can ask some questions. For example, you can ask, is there a way in which the lower dimensional physics really look lower dimensional is just some rewriting of the higher D theory, which is something you can quantify by asking what is the mass scale of this Kaluza Klein particle compared to, say, the scale of the cosmological constant of in the lower dimensional vacuum. And for example, this question is named as the problem of scale separation in compactifications, where a vacuum is said to be scale separation if there is a high hierarchy between the massive of the Kaluza Klein fields and the mass of the cosmological constant. And it turns out that this is a highly non-trivial problem in the sense that if you start with the more say standard higher dimensional theories like 10 or 11 dimensional supergravity that we get from string theory, then if you only have classical sources that source you on the ground, then it's really hard to get vacuum which are scale separated. And indeed, the vast majority of examples don't have this property. There are some proposed constructions that use some effect, either non-classical effects or some exotic objects that have negative tension, which are part of the string theory. But there is still debate going on whether these constructions are under control enough to claim that they have scale separation. So it's in general a hard problem. It's an important one whenever you have a theory of extra dimension, because you would like to be able to use it to describe lower dimensional physics, if you want to make sense of it.
And so this very light spin-2 fields question, there you want like a finite set of light spin-2 fields. That's why you phrase the question as having, say, one go to 0 and the other.
Yes. So I didn't get there yet. Thanks. There is another question you can ask when you have this tower. Among this tower, you have spin-2 fields in general, among the Kaluza Klein fields, and then there you can ask the following question: can I have some very light spin-2 fields, or for example, can I have just a few that are lights, say just a single very light spin-2 field, or do I need to get the full tower that becomes light, or can I just have a finite number of them? And this can be useful in case you want to embed, say, massive gravity models in higher dimensional theories and obtain, say, the very light spin-2 field from the Kaluza Klein tower.
Can I ask the question?
Questions, yeah.
Saab, yeah.
Sorry. Are you asking this question in string theory or more generally?
Sorry, I can't.
Sorry, Saab, there's some problem with the audio. Hang on a second.
Try again.
Can you hear me now?
Yes. Right.
Okay. Are you asking the question in string theory or more generally?
So what I'm going to present is general in the sense that we are just going to use the Einstein equation for a generic theory. But in the examples that we have in mind, then yes, we are going to think about string theory, and in particular, starting from 10 or 11 dimensional supergravities.
So the higher dimensional theory should have 0 cosmological constant.
That's a possibility, or for example, if you can think of massive type 2A, it has a kind of cosmological constant that is still included in this discussion.
I see. Good. Thank you.
Okay. And other reasons you might be interested in studying the Kaluza Klein spectrum is if you are interested in holography, where in the holographic dual you will have the masses of this field give you some information about the dimension of the operators in the dual. So these are just motivation for why one could be interested in Kaluza Klein scale, and it doesn't work.
Maybe click on that.
Sorry, screen maybe, yeah. Sorry.
Okay.
Yeah.
And good. And our approach, as I said, is we are going to try to have a top-down approach. So we are going to consider a fixed higher dimensional theory of gravity, which we are going to specify in a moment. And we would like to be rigorous in the sense that we like to find theorems on what's allowed for the KK spectrum. Now, in general, if one wants to be as general as possible, this is a hard question. And the reason is that the masses of the Kaluza Klein fields are given by the eigenvalues of some differential operator defined on the compact space. And just to fix the notation, we are assuming that higher dimensional spacetime decomposes in the lower dimensional spacetime and a compact space. And in general, you can have also what's called as a warp factor. This is compatible with the symmetries of a lower dimensional vacuum. And this is a general function that depends on the coordinates of the internal space. That's the most general vacuum compactification you can have starting from higher dimensions. And the point is that the masses of the Kaluza Klein fields are given by eigenvalues of some differential operators defined in the internal space. But even just, and to find the masses, we need to compute the eigenvalues. But even just the operators themselves are not known in general for a general compactifications. There are some results when you have some symmetry. For example, if there is no warping, and that's a class of compactification, you can assume that this A is 0, so you just have a product. Then there are results here. You can, starting from the 80s, these are kind of computations that have been done. You can, for example, for Freeman-Rubin compactification or for compactifications on homogeneous spaces, then you can write down the full set of operators and even diagonalize them, thanks to a lot of symmetry that you have in those cases. Or actually, you can even find the spectrum of some of these operators. An operator that comes often in the A equals 0 case is just a Laplacian, even in cases without much symmetry. You can use some numerical techniques, like has been done with people here, or in Calabi-House, or even with some bootstrap-like techniques for computing the spectrum of the Laplacian on Riemann surfaces. But all of this is when warping is 0, and you know the operators at least. In general, for a warped compactifications, there are no complete Kaluza Klein spectra known, except for, again, when you have enough symmetry, in particular enough supersymmetry, where you can use some beautiful tools of exceptional field theories. But the current status of those is that they work when you have maximal supersymmetry in the reduced theory. So they allow the computation of Kaluza Klein spectrum with warping, but they are restricted to supersymmetry. So if you want to be general, it seems that we are out of luck because it's in general probably it's really hard. But however, the situation is simpler if you focus just on the spin 2 part of the Kaluza Klein spectrum. The spin 2 Kaluza Klein spectrum is what arises as a perturbation of the space-time part of the metric around the vacuum. And here there is a beautiful results by the authors here in the slide that tells you that for a general compactification with warping, this is the operator that gives the masses of the Kaluza Klein fields. So of course, to compute these masses, you need to know a specific solution so that you plug the metric and the warp factor, but at least the form is known in general for the spin 2 field.
Sorry, just to make sure I understand. So here, you're only considering a metric, right? There's no other background field?
No, there is, you can have all the field, also the flux is say turned on, but the spin 2 fields is not sensitive to it. The masses of the Kaluza Klein spin 2 fields only depend on this operator that only depends on the warping and the metric, even if your compactification has all possible fluxes turned on.
So you're assuming small net reaction from any other field to the metric.
No, this is a general. So this is a general solution to the equations of motion. So you can assume that you are in a general solution of the equations of motion. And if you consider the masses of fluctuations of the space-time metric around a general configuration, this is the operator that gives the masses for those fluctuations.
Just to make sure I understand, is this because it's a scalar fluctuation on the internal space?
No, it's because the spin. So it comes because the spin to fields. If you choose the gauge appropriately, you can say that you can choose the space-time fluctuation to be transverse and traceless, and then you can show that there are no other things that can mix with this part of the fluctuation on the space-time. And so
I mean, if I think about like a form field with a kinetic term, that kinetic term is decoupling from this fluctuation for some
yes,
reason?
because all the couplings that you can write down are actually zero if you integrate by parts and use that is transverse and traceless, this fluctuation.
Oh, interesting. Okay, good, thank you.
And yeah, this has been proven in general. And and thanks to this property, people have been able to compute the Kaluza Klein spectrum even for more general compactifications, even with fluxes, the spin to spectrum, even where there is not much symmetry. Just because the operator is known, and then you can start talking about its eigenvalue for other ordered compactifications. And for example, this property has been used to show that for the supersymmetric ADS7 and ADS6 solutions, in general, you don't have scale separation. Okay, so that's the operator we are interested in. And we would like to know about its spectrum in general. And we can already start having some guess of what this could depend on. It will depend certainly on the internal geometry. And in particular, there are some mass scale that you can write. You can think of it depending on some way on the longest distance that you can have on the internal space, its diameter, or an appropriate power of the volume. And however, we don't want, our approach here is not to change arbitrarily these quantities and check what the spectrum is, but we want to use the fact that the geometry is fixed by the Einstein equation once you are specifying your theory. You specify the theory, you have some matter content, and then you have the Einstein equation that constrain the geometry, and in particular through the curvature. And so we want to use this information to constrain the spin to fields. To give you an idea of how one can try to do something like that, we can look at some classical Riemannian theorems in Riemannian geometry. For example, suppose, now let's forget about the work, suppose you are just in Riemannian geometry, and suppose you are able to show in some way that the Ricci tensor is bounded from below by a positive constant. This will not be true in general, but let's assume it's the case. Then there are standard theorems in Riemannian geometry that tell you, for example, that diameter is bounded from above by the same constant, or that the first non-trivial eigenvalue of the standard Laplacian is bounded from below. And of course, this is not, we cannot apply this theory directly because we are, as we're going to see, we cannot bound the Ricci tensor, for sure not with a positive constant. And also, in general, we are not interested in the eigenvalues of the standard Laplacian. However, I'm going to show these two probably will talk to each other in the following. And this is roughly the strategy we are trying to use. We will try to find some bound on some geometric quantity that help us finding a bound on the spin to fields. Okay? Good. Okay, so these are enough words. Let's start with the equations. So we are considering general higher dimensional gravitational theory with a standard kinetic term. So we have a general Einstein-Hilbert action in higher dimensions, and we are considering compactifications. Again, we can define things such that the more general metric is this form, where the vacuum is specified by its cosmological constant in some maximally symmetric space. And then we have the work function, that's a general function of the internal space, and this is the compact space, which I'm going to call the internal space. Now, the first thing you can do is, well, let's write down the Einstein equations. In particular, you can write down in this form, which is easier for this kind of analysis. And then you can plug the ansatz. If you do that, you get two sets of equations. The ones with legs along the space-time, extended space-time, just calling here a vacuum equation, and then the equations along the internal space. And so let's focus on the vacuum equation. This is it's a linear differential equation, but it's simple in the sense that it's a scalar equation at least. And this is because a vacuum is maximally symmetric, so we can take a trace and without losing any information. And this equation turns out that it's very powerful in constraining the kind of compactifications you can have. And for example, you can use it to prove that if you only consider classical sources like form fluxes or scalar fields, or but without allowing yourself to use localized objects with negative tensions, such as orientable planes in string theory, then under this hypothesis, you can prove from this equation basically that the cosmological constant has to be negative. And this is there are some famous theorems. And all these can be obtained by this vacuum equation. And now we would like to do something similar, but for the internal equations. But there we cannot just take a trace because we are not assuming any symmetry on the internal space.
So can you say the constraint on the sources is more covariantly organized as an energy condition? Can you remind us which energy condition it is?
No, good. So it's a relative of an energy condition. Often you can say that what's enough to prove that lambda is negative, the strong energy condition in high energy theory, but that's not entirely true. It excludes most of this proves it for most of the sources, but for example, you wouldn't prove it for a higher dimensional cosmological constant like the Roman's mass, and that has to be excluded separately in another way. But if you don't have, because a higher dimensional cosmological constant can violate the strong energy condition, so if you exclude that case, then it's enough. Otherwise, for that, you can, in mass type 2 theory, you can exclude it in a different way. And okay. And so we would like to analyze this equation. If we take the trace, we can constrain, say, the Ricci scalar. But again, if you have no symmetry, this is in general a two-week constraint on the geometry. Okay, so let's try to not take a trace and consider it completely. So we would like to find some bound on some geometric quantity. And it seems that we are in trouble because we have some terms that don't have a definite sign. So it's hard to bound them. For example, this second derivative in general can have any sign and change in the internal space. Well, we can start getting rid of one of those by using the other equation, the vacuum equation, and we get the expression here in the slide. And we still have a second derivative here, which we will worry about it later. But the right-hand side is actually nicer now. And well, we have the first line, we just have the cosmological constant. We can control its sign. And the second term is just, as a definite sign, is minus a square. And the third side, so let's give it a name. This is the work function. If there are no singularities, this function will be bounded in a compact space, and its gradient will be bounded as well. And so let's give it a name to this bounded. Let's define this constant sigma. And okay, and the third line is a peculiar combination of stress energy tensors. Is a stress energy tensor along the internal space minus this trace along the external space. And my claim here is that this combination is non-negative. And In particular, it's non-negative for all classical sources, even like form fluxes of any dimension, and for say for scalar fields, and even for localized objects like branes. But it's not true for localized objects with negative dimension again. And since this thing has a flavor of an energy condition, let's give it a name. Name can be the reduced energy condition, because it's kind of energy condition that only makes sense when you're reducing the theory. And also, to come back to your question, you can prove that actually the Roma's mass satisfies this directly, while it doesn't satisfy the strong energy condition. So it's not directly a consequence of the strong energy condition. Okay, and so you can prove this by writing down your matter content and then deriving stress energy tensor, and then with some algebra you prove this inequality. Okay, and so we're going to restrict to cases of theories that satisfy this energy condition, which is pretty broad because most classical sources do it.
Sorry, does any potential satisfy this, or just the Roman's case?
That's a good question. Let's see. I don't know about potentials.
I mean, the Roman's mass is really a potential for the dilaton.
Yeah, so in that case, yes. Another thing is that the supercritical term that you will get in string theory, if you are allowed to be not in the critical dimension, that's also kind of potential for the dilaton and also satisfies this condition. I don't know about more general stuff. Huh?
Thank you.
I guess one can write down and see what classes satisfy this. That's a good point. And if you are in a theory that satisfies this, then we have proven this inequality. We've proven that a certain combination of the Ricci tensor and the Hessian of the work function, this f is just directly related to the work function, it's bounded from below by a certain negative constant, which depends on the cosmological constant and the bound on the gradient of the work factor. And since we are now we are not allowing for row planes, we are also in the hypothesis of the Nunez-Zergo theorem, so that the cosmological constant is not positive. So for the rest of the talk, I'm going to assume that is negative. Okay, so we still didn't manage to bound the Ricci tensor, but at least we have found the bound in this particular tensor. And it turns out that actually this is a tensor that's already been studied by a mathematician in the context of what's called Bakry Émery geometry, from the names of two French mathematicians, or B geometry, to avoid to mispronounce their name again. And where B geometry is just a generalization of Riemannian geometry, where you have your manifold metric, and you also have a certain positive function defined on it, which you can think of it as a weight that weights the integrals, like the volumes. In this framework, it turns out that this peculiar tensor is very powerful in constraining the geometry. And in particular, so we have found a lower bound to this tensor. I'm going to use the shorthand HF for this modified Ricci tensor. And in this mathematical framework, you can show that mathematicians have shown that this tensor controls the spectrum of a certain operator, which is a Laplacian modified with the same function f. And this function f, so you can understand how this Laplacian comes from, and this is because this is the natural operator, which is self-adjoint with respect to the L2 measure with this extra weight function into the f. And now we can imagine where we are going with this. And it turns out that this is precisely the operator that gives the masses of spin-2 fields for warped compactifications. And so this operator is precisely what we had defined before, and its eigenvalues will be the masses of the spin-2 field for a general compactification with warping. So thanks to these properties, we can now go to the math literature and see what mathematicians have already found about bounds on the eigenvalues for this operator. And turns out that there are some nice results that are interesting for us. And in particular, these are bounds that you can find these works by Sanejad and Setti and Shalambu, Yu, and Rowlett. And these are bounds on all the eigenvalues. For example, these two theorems, theorems 1 and 2, which for us translate in eigenvalues on all the Kaluza Klein, masses of the spin 2 Kaluza Klein fields. And these bounds depend on this constant that we just computed from the equation of motion, and some other geometrical quantity. For example, this theorem 1 depends on this warped volume, which is
So what is little n?
little n is the dimension of the manifold.
The internal manifold?
Yeah, so 6 or 7, say, for simplification of string theory.
So but this constant alpha of n and beta of n, they only depend on n but not the actual manifold?
Precisely. Alpha, beta, gamma, and c, you can estimate them in general. There are some bounds on this constant in the paper, but yeah, they are universal in this sense. They only depend on the dimension. And so this is a theorem that bounds in terms of this volume, which is from a physical perspective, just a product of the higher dimensional Planck's mass and the Planck's mass of the real string. Or these are bounds in terms of the diameter. Okay.
So that the first line is like the Weil's law for the growth of eigen.
Yes, precisely. But also for
with the
this
offset.
modified
Yeah.
fraction, yeah.
Uh-huh.
And okay, so these are the results we have so far for this class for this operator. And so this constrains the speed to scale in general, even with warping. And then you can start asking whether you can use it to prove, for example, that there is or there is not scale separation in this, say, by using just classical sources. And fortunately, these bounds alone are not enough. These give a constraint between the precise relation between the spin 2 fields and, say, this warped volume or the diameter. But to be able to prove scale separation or exclude it, you need to know something more about the geometry. And for example, you can understand this, for example, by looking at the volume, at the bound in terms of the volume. There you can make this bound weaker and weaker if you have a space with, say, a fixed curvature like a sphere, and you start taking quotients. You can make the volume arbitrarily small, but and so this make this theorem weaker and weaker. But this will not affect much the diameter, and so it seems that these are more promising to prove or disprove such a theorem, such a property in general.
Can you give us some intuition why taking quotients can change the volume but not the diameter?
Because you cannot make all the directions small. You're making some directions small, but there are still large ones. Like if you take a quotient of a sphere, say in S7, you write the S1 fibration, then you can make the S1 very small, let's say an S3, the same. But the S2 remains the same, and the diameter is the largest distance that you have in your manifold. So the volume will be more or less a product of this of these lengths, but the diameter is the largest that you have. So by making one direction small, you can make the product small, but you not make the largest one small. And indeed, in very recent work, it has been noticed that by taking quotients of spheres, you don't really make you cannot make the diameter lower than a certain threshold. And this has also been proven true in some example in Sasaki-Einstein spaces. And it has been conjectured to be true for Einstein spaces in general, that they have a lower bound on the diameter. And in this recent paper. And this will go very nicely with these theorems that, however, are much more general, since they work for general solution of the Einstein equation, not just Einstein space. But you can see if you can prove a bound on the diameter, then you have an upper bound, say, on the Kaluza Klein scale.
So how is the warping coming into the story? Just through the volume?
So the warping enters through this constant here. So in the volume and in this constant sigma, which is the basically the maximum of the gradient of the working in the internal space.
Maximum of the gradient of the work. Okay, I see. So that's something, for example, in flux vacuum, that would be determined by the amount of flux that you could throw in. And so by some topological property of the space, say.
Yeah, so the amount of flux will control both the volume of the volume without warping, probably of the manifold, depending on the compactification, and can make the space large or big, so even just control the diameter itself, but it can have also an effect on the warping, yes.
I see.
Yes, depends on the details of the compactification.
Bruno, can you clarify, the diameter there, is the diameter defined using F as well?
No, the diameter is the
Standard diameter,
standard
but
diameter.
volume is defined using F.
Yes. It's just the measure that's modified, not the distance function. Okay, and so these are theorems that bound the Kaluza Klein spectrum quite in general, but there is still a limitation. Limitation is that these are obtained by using some math theorems that are proven in the smooth setting. And however, we would like to say something more. And this is because we know that in compactifications, a lot of physics, there is a lot of non-trivial physics when you have some sources, like D-brane sources. And those in general introduce, in the supergravity limit, in mathematics, say, introduce some singularities. So we would like to have some theorems that tell us properties of the Kaluza Klein spectrum, even when there are such singularities. And we cannot apply directly the theorem I just showed because those are formulated in the smooth setting. So if you want to use some mathematical theory, we need to look for theorems that are proven in a more general setting, where the standard notion of, say, of curvature is not defined. And it looks like that mathematicians have also thought about these kind of problems. And what they teach us is that we need what's called a synthetic definition for the curvature, which means the following. Suppose, let's forget about so we would like to say that this tensor is bounded from below by a constant, but there can be singularities so that this can even be ill-defined. And a synthetic definition is a way to put bounds that doesn't require you to be able to take derivatives. For example, if you're just trying to define what is a convex function, then you can do it in two ways. You can say, well, the second derivative is non-negative, or you can say, well, I take the function, I take 2 points in the function, I draw the segment that connects them, and I require that the function always lies below this segment. Mathematicians call this a synthetic definition, while the first one is an analytic definition. And the second one is much more general. They don't require the function to be differentiable, not even continuous. It's harder to prove if you give you a function, but it's a more general definition. And so mathematicians try to find this kind of definition also for geometric quantities, like the Ricci tensor. And they have done this in the context of what's called as optimal transport theory. This is a huge subject. I'm not going to try do justice to this subject here. I just want to give you some hint of how this might be related to curvature. And so let's try to do that. So now forget about the Riemannian geometry and our Riemannian manifold. Let's assume that we have a very general space. Can be just a set with some a distance function, a distance defined of it, and a measure. Mathematicians call this a metric measure space, which can be very general, can be discrete. There is not even a notion of dimensions defined on it. And now, suppose in this space you want to move some mass from one place to the other. So, so you have a probability distribution which you want to morph into another probability distribution by minimizing a certain notion of cost, but the cost of moving one bit of mass from one place to the other is given by the distance function that you have on your space. An example can be the following. Suppose you have a city and you have some bakeries that produce bread, and you want to move the bread from the bakeries to the shops that need to sell the bread. And each bakery can produce a certain fixed amount of bread, and each shop can sell a certain amount of bread each day. You want to move the bread, and by minimizing the total cost of moving stuff around in your city, say the distance traveled. And so you need to find a way where to move each piece of bread from one shop, bakery to the shop. And this is why this is in the context of optimal transport theory. And in formulas, what I've just said is this is defining distance on the space of probability distribution on your original space, which depends on the distance that you have in your underlying space, not just the distance between the probability distributions. It has a name, it's called Kantorovich-Wasserstedt distance. This is just in formulas what I just defined. So we're almost to the curvature. Now, we have this very general setting. We have space, a distance, and a measure, and we have defined a distance on the space of probability distributions. We didn't use the measure yet, and this is the crucial point to get to the curvature. And mathematicians in this context define what they call the relative entropy, which is an entropy that you so given a probability distribution, you define its relative entropy relative to the measure that's fixed on your space in this way. And this is a certain definition, it's a functional, and then you can start asking questions about this functional. For example, you can ask, is this convex? Or a bit more general than that, is this K convex? Which is the property here in the slide. So it's like the definition of convexity, but it's a bit more complicated because now this is a function of the space of probability distribution. So we need so we fix two probability distributions and we want to see if this function is convex. So we need first a geodesics that connects them. It is a geodesics with respect to the Wasserstedt distance and the distance on the space of distribution. And then you can ask if this function is convex, K convex, which means if it satisfies this property. This is a bit abstract, it's a kind of convexity for the entropy. And it turns out that this property, this is K, with a fixed K, is enough to characterize a class of spaces, which are called RCD spaces, RCD K infinity in this case, where this stands for Riemann curvature dimension. So these are spaces which are quite general. They only have a synthetic notion of curvature being bounded from below by a constant K, and of dimension being bounded from above by, in this case, by infinity, on this definition. And the K is the same. And this is interesting for us because this is the synthetic notion we were looking for. In particular, this means that if you take the smooth limit of all of these, and say if you're interested in now, you can go back to our Riemannian setting with the distance just being the Riemannian distance, and the measure being the volume one induced by the metric and possibly a positive weight function defined on it. Well, this is just the synthetic definition of a Ricci, this modified Ricci tensor being bounded from below by the same constant K.
How do you compute S?
So S is defined like this.
So, like, given the analytic version, how would you compute S? It's some kind of integral of R?
Well, S is the entropy of a given probability distribution. Is the fact that it is K convex, it's related to this notion of curvature. If you're asking how to prove
I'm just
these,
I'm asking for the analog of, so in the convex function synthetic versus analytic definition, you know, taking the limit as you could as you make the segment smaller, you could see how the integrated version is related to the differential. I'm asking what the analog of that is.
It's a good point. To be honest, I don't know the details because this this S is evaluated along geodesics in the space of probability distribution.
Yeah.
And those depend also on the underlying geometry. And there is some very non-trivial, there are some very non-trivial steps to go from these to these.
But I guess I'm asking also if you're suggesting that the Ricci tensor has some entropic interpretation.
That's a very good question. It looks like, it would be very nice if there is some deeper connection here, which I don't know. It seems there is something, at least it's kind of non-trivial that this implies this. And yeah, but I don't know. It's an open question. I think it's an interesting question. If we can get say the Einstein equation or from just imposing properties of this entropy. I'm just noticing that all this connection up to this stage, but I cannot say more. And okay, now this is a synthetic definition, so it gives a definition of this tensor for general spaces. But for it to be useful, we would like to be that in this class we have the spaces, the singular spaces we care about, and this can be proved as we've done with our friends here. So you can prove that the singularities that you get from D-branes, or more general for objects with positive tension, are in this class. At least for the singularities that you see from these objects in flat space. It looks like the same hold also in asymptotic cases, so where the manifold, these are not just the full singularity in flat space, but you have some manifold that has some points where the singularity looks like the ones that you know in flat space. Seems that they also satisfy this property. They are in this class, but this, at least for now, it seems not to be really the case for when the sources have negative tension, so like coplanes. At least we can now say that if you can look in the literature in optimal transport theory and in the RCD, particularly the RCD literature, and the eigenvalue bounds that we find there will also hold for compactification with sources like branes. And that's what we are going to do next.
Can I ask a question right here? Do you have a way of defining? Do you see any way of defining this relative entropy in a conformal field theory associated to say one of these backgrounds? Like if you imagine some sigma model CFT, would there be a natural definition of this?
That's a good point. I don't see it right now. It might be that there is some relation to some entropy on the CFT. I think
it's not obvious to me what it could be.
Yeah, no, not even to me. To be honest, yeah.
Okay, so thank you.
Yeah. These are all good questions. And yeah. Okay, are there more questions here? Okay. And good. Now, let's see a class of bounds that you can prove in this more general mathematical setting. Now, suppose this class of bounds uses a definition of a certain geometric quantity, so that is this one in the slide, which has been defined in the simple case, in the purely Riemannian case by Cheeger, and is known as Cheeger constant, and is defined as follows. Now, suppose I give you a manifold and I ask you to chop it in two pieces, and for each of the two pieces to compute these quotients, or this quotient. Now assume that f is 0. This is just the volume of the boundary of the submanifold that you have obtained, divided by the volume of the submanifold itself. And you need to you pick the highest ratio you found between the two pieces, and then you do it for all the possible choppings and keep the lowest value that you find in this way. in the Riemannian setting, this is called, so f equals 0, this is called a Cheeger constant. And for example, this has been introduced by Cheeger, and you can see a picture from its original paper. And this is a manifold that has a very small Cheeger constant. You can see it why. It is because if you chop it, cutting it just precisely here in the middle, where there is this small neck, then the denominator will be small, and the numerator will be small, and the denominator will be big, and so we'll get a very small ratio. Or here is another example of a manifold that has this. But the definition also allows for you to include a measure, and it also holds for more general RCD spaces. Now, why this is a useful definition? Well, it's because this constant is powerful in the sense that it's able to strongly constrain the first eigenvalue of the Laplacian, or in this case of this modified Laplacian. And so for us, the first massive spin-to field of the KK tower, and it constrains it pretty tightly. And this is because you can put both a lower bound and an upper bound on the first eigenvalue. So if you happen to have a manifold, possibly with warping, that has a very small Cheeger constant, then you can say that the first spin-to field is very light. And this comes from the lower bound on this modified Ricci tensor and from a theorem by the Ponti and Mondino in this RGD setting. So it holds also for compactification with sources. And I'm going to see the physical implications of this in a moment, but you also say that this can be generalized, and also in order to also bound the higher eigenvalues. And to do that, you need a generalization of this Cheeger constant. And this generalization is quite natural. This time, instead of chopping the manifold into pieces, you chop it into k pieces and compute these ratios. And this defines all the higher order Cheeger constants. And in terms of this, we have proven that you can bound the higher eigenvalues, so the higher spin-to fields, both from below and from above.
What's with the k to the -6 factor?
It's there.
The bound becomes weak as k gets large, or should I think
Well,
that,
this is-
or should I think that hk compensates for it?
Well, these are independent. So k is the kth element of the tower,
Yes, I understand.
and
But
hk can
you
be,
also chop into k pieces, yeah?
yes. Then it depends on the manifold. You can have a manifold which say the first h1, h2, h3 are small and the other high.
But I'm trying to understand if this bound is becoming worse as k is going to infinity just because of the k to the -6 factor. Like, is there some kind of natural scaling with k of hk that is compensating? Otherwise, it seems like for large k, you're just proving that mk squared is greater than 0.
Yes, that's a good point. I guess it's a general rule that it becomes harder to bound the higher ones. Also,
But for
for
instance,
the other,
mk plus 1 is heavier than mk, but it doesn't look obvious from this formula.
well, oh, okay, yeah, but because good. So you're asking if h1 is always smaller than h2, say?
For instance, yeah.
I will say yes. Because if you can cut it in 3 pieces, you can also
Is it
cut it
allowed
into
that the
pieces by putting
BKs
2 of them together.
Yeah, you can consider 2 of them as one piece in
Yeah.
this. Yeah.
Yeah, that's a good question. And okay, and a lower bound and an upper bound. As for the first one, the second depends on the curvature, but the first one doesn't. And okay, so putting these together, you can now start asking questions, want to say physical questions about the spin-to fields. For example, you can show that if the first spin-to field is above the, say, the scale of the cosmological constant plus this constant sigma, then it also puts an upper bound on the higher spin to fields. And this means the following. Suppose now you have the first spin to field, and you want to make it very light. You have some mechanism for getting M1 that goes to 0. Then this bound tells you that also the other elements of the spin to tower are going to become very light. And this is an agreement with some spin to conjectures that differ in details, but what they tell in general is that when if you have an effective theory with a light spin to field, you expect that it breaks down at a certain point in the limit where you send this light spin to field to 0, its mass to 0, because there is some tower of spin to fields or higher that is becoming very light. And you can see that this proves it in a certain regime, in the sense that when you're sending M1 to 0, you're getting also that the other elements of the towers are going to 0. However, it is an agreement, but it's true only in this regime. If M1 is going to become light, and once it crosses the threshold of the cosmological constant, then this is not true anymore in general. You can have a situation where the whole tower becomes light, but it's not required. And indeed, if your manifold has a H1, the Cheeger constant that goes to 0, but the others remain fixed, H2 and others remain fixed, then you can have an arbitrarily high ratio for the second element of the tower and the first one that's becoming very light. Yes?
Is M1 literally lightest mass, or lightest one be above the possible zero?
Good, that's a very good question. So if the space has finite warped volume, so if the lower dimensional theory has finite Planck's mass, then you always have the zero mode, the massless graviton. But all these theorems also work in the case where the mass Planck, the reduced Planck's mass is infinite, so the space has infinite warped volume, and so this will become a bound on the first non-trivial one. But if you don't have the zero mode, this is just a bound on the first one. It's a very good point. And this is relevant if you're interested in embedding, say, bi-gravity theories or just massive theories of gravity. Yeah. And so if you can achieve this limit by keeping the second modified Cheeger constant fixed and the curvature bound, then you can have an arbitrarily high separation. And this is realized in string compactification, as I'm going to show in a moment. And so the KK tower doesn't satisfy this conjecture, but the conjecture don't tell you exactly which is the tower that's becoming very light. So an open question is whether in this limit of H1 going to 0, whether there are other spin-2 fields that are not in the KK tower that can become very light. And this is still an open question. We need to study more, but this is what we can prove in the KK spectrum. Now, just to be quick, now I want to show you some examples that realize all of these. These are not just some geometric manipulation, but there are explicit compactifications that do that. One example is this class of n equal 4 against 4 compactifications in type 2b by Bacchus and Lavdas, and then defined by Lavdas and Lust, where the internal space has this shape of having two large, they call them bags, connected by a thin bridge. And what they've shown is that they've computed the first spin-2 field, the mass of the first spin-2 field, and then they found it's very light. And now you know understand why in general, because it's a consequence of the first Cheeger constant going to 0. And in this setup, you can also have an holographic description where basically the holographic dual of these, you can think of it as two CFT trees connected by a CFT4. And in this case, the Cheeger constant is proportional to the degrees of freedom of these CFTs. And another class of compactifications is given by compactifications on Riemann surfaces, like n equal to ADS5 compactifications in M-theory, or similar, even non-supersymmetric compactifications. And here you can show that the light part of the spectrum is the light part of the standard Laplacian on the Riemann surface for this compactification, and then you can just compute the Cheeger constant for in your Riemann surface. And then it's also nice to see this, to explicitly see this Cheeger constant, because for a Riemann surface of a given genus, we know that there is a natural natural splitting in terms of decomposition in terms of pair of bands. And this pair of bands can have the geodesic length at the end of the pair of bands to be any arbitrary real number, a positive real number in the length. And so you can tune them as you like. This doesn't change the curvature. And you can tune to G minus 2 of them. This means that you can play with, these are precisely the piece in which you can chop your manifold to define the Cheeger constant. And this means that you can tune the first 2G minus 3 spin 2 fields in a Riemann surface of genus G to be whatever you like. And that's another example of how to use this, how this is realized. And coming to the question before, yes, all these also holds when there is no massless graviton. So this is a precise way to obtain massive embedding of massive gravity models in string theory through the Kaluza Klein power. And okay, so let me just leave here a recap. We have shown that for general gravitational theories, and that satisfy this energy condition, which is quite general. Then there is this lower bound on this tensor, and this can control the spin to spectrum in terms of the diameter of the worked volume. And it's also, there is a way also to prove these bounds in a more general context that allowed to regularly deal with the singularities, like brane singularities. And we can also find mathematical theorems that constrain the spectrum in this case. And all of this is realized in explicit string compactifications. Here, let me thank you.
Questions?
I guess one just simple question is that this bound doesn't apply, as you said, if your compactification includes negative tension branes, for example.
Yes. Yes, those violate these, and they also seem to be outside of this class of that has this notion of synthetic notion of curvature being bounded below. Yes, we are our work in progress. We have to get the task of also understanding what happens in those cases. But yes, so far, yes, those are excluded.
Have you tried including the R squared terms in heterotic, going beyond 2 derivatives?
That's a good question. No, we haven't. So here we are using a standard Einstein-Hilbert kinetic term. We didn't consider higher derivative curvature. Those will modify the Einstein equation, and yeah, we didn't play with that yet. We don't know what that implies. But it's yeah.
Because it looks like, this is nice enough. It looks like it might be tractable to include them. And in some sense, that is including the orientable physics of a type 2 dual.
Mm-hmm.
Most of the features are present there.
Mm-hmm.
There we go. It would be kind of neat. Sorry, can I ask you a different question? What is your schedule? Are you here tomorrow as well?
No, actually, no. At least, unless you want to meet very, very early in the morning.
I actually will be here very, very early in the morning.
Okay.
So that might be okay. Maybe I'll email you and we can coordinate something. Yeah.
Thanks.
Great. Well, if there are no more questions, let's thank Bruno again.
Thanks.